Okay, so today, echoes. And specifically today I'm talking about trains of echoes where you've done a series of RF pulses. And the lecture, this lecture is seriously out of order. It assumes the main lecture, the main spin echo lecture. And so I'm just going to quickly sort of introduce the main lecture topic, and then I'll go over it more in the 9 o'clock. So why do I call it an echo? And so what this comes from is really just strictly empirical observations. Basically what people did is they just did an RF pulse and then record what comes out. And if you just do one RF pulse, you get like a signal that sort of, comes out and dies away. And so what they did was, let's just do another one. I don't know if they did it initially by accident or were trying to do it, but if you just do another RF pulse, it depends on what angle it is. That one might make a signal like that, but then if you just go the same distance in time, you see the signal just appears out of no place. And if you didn't do this one, it wouldn't occur. And why is it called an echo? Well, because it's the exact timing of it just depends on where you put this second pulse. So it just looks like an echo of the second pulse. And you can just do this with, a sample of salt water or something. So that's basically the idea of an echo, and the fact that it was, completely controlled by exactly when you did the second pulse immediately suggested trying to think of some way that we could sort of generate this coherent magnetization. Because why does the signal go away? Well, there's two things. It's the jostling part, that's the T2 decay, and then there's the T2 prime decay, which is this slight differences in the magnetic field from different place to place, which causes the signal to get out of phase. And so that's really what the whole echo picture is about. And the one I'll talk about in the main lecture is a special case where you do a 90-degree pulse, and that causes a signal, and then you do a 180-degree pulse. And a 180-degree pulse means flip the magnetization, completely down. So if we make a little drawing over here, so here's our starting magnetization. So we could flip that starting magnetization to something like that, but it's possible to just go all the way around and reverse it like that. So you could either do, you could do a flip like that, or you can just do a flip that goes all the way around to 180. And if you do that, you shouldn't have any XY component. So this is the Z direction, and this is the XY direction here. And so that means you shouldn't get any signal. So you don't get any signal, but then just like clockwork, that amount of time afterwards, so if that's, tau amount of time, you just go that amount of time afterwards, and right at that point, with no stimulus, you see this echo comes up. So that's spin echo. There's other kinds of echo. We'll talk about two different kinds, spin echo and stimulated echo today. But then there's also gradient echo. I'll talk about that next week. So that's the basic. So that's the main lecture is to try to describe why that's occurring, and just in a just preview, why does it occur? Well, what happens is if you start off with the magnetization all lined up because the RF swept everybody into the same phase, what happens over time is it starts to spread out because there's differences in B0 like that. And if you wait long enough, there's still magnetization left, but it's all spread out like that, like in a disk. And when that situation happens, you don't get any signal. But you want to distinguish that situation from another situation, which is actually no magnetization, no local magnetization. So both of those sum to 0. No local transverse magnetization, and tons of transverse magnetization that is, however, all out of phase with itself. And how does spin echo work? Well, you just take this thing and sort of flip it over, and then what happens is whoever was ahead is now behind. And then you wait exactly the same amount of time, and sure enough, everybody catches up again. And so that's basically the idea of how spin echo works. So pretty much virtually all MRI data is collected with an echo of some kind. And there's some spectroscopy is collected, can be collected without an echo, but usually even spectroscopy is collected using an echo. So pretty much all the data is collected using an echo. So that's why we talk about it. So it turns out it's really easy to make echoes. And in fact, that's the problem. You can make thousands of echoes, no problem. And we'll just talk about, so this is a spin echo that had 2 pulses. What we're going to talk about is just 3 pulses. So if you make 3 pulses, you'll get 4 echoes after the 3 pulses, and another echo in between the 2 pulses. So there'll be like 5 echoes total from 3 pulses. If you do 6 pulses, you get hundreds of echoes. And so part of the problem of MRI is managing the echoes, because when you're actually collecting MRI data, you need, for a high-resolution 3D scan, you need 10 million data points. That's a lot of echoes. It's a lot of RF pulses, thousands and thousands of RF pulses, and so you're getting millions of echoes. And so one of the problems is kind of, as we'll see, is kind of managing the echoes. It's really easy to make an echo. So we'll start with a big diagram here of our. Let's put this up pretty high. So here's the RF stimulation. So we're just doing three RF stimuli. So the first RF is a 90-degree pulse here, and we'll call that guy. So in MRI, when they want to refer to a pulse that's not, that isn't a 90-degree pulse. So when they want to refer to a pulse that's just any old angle, they use alpha, meaning like it could be a 30-degree pulse, meaning it only went like 30 degrees, or it could be a 90, or it could be whatever. It doesn't have to be 90 or 180. And so that's the first pulse that doesn't have to be 90 or 180. It's just whatever. And so when we look at the, it's about down here. So here's the signal that we're getting out of the sample. We'll just call it a sample. So that signal is going to be an FID. So it's a T2 star decay. So here's that signal. So that's stimulated by that pulse. And if we didn't do anything else, that's all that would happen. Nothing would happen down the line. So then plan B is do another pulse. So here's another pulse, and this one doesn't have to be 90 or 180, so we'll call that one alpha 2. And the amount of time between that we'll call tau 1. So tau 1 amount of time. And so here's our first pulse, and so then here's the second pulse. And since it's not particularly 180, so if it was 180 exactly, then it shouldn't make any signal because there would be no transverse magnetization. But since it's not necessarily 180, we'll get a signal out of that guy too. So there's a second FID. And then the first thing that happens is we go, that amount of time forward, and we get an echo. And so that guy is our first echo. So it will come up, it's a pretty big echo. It's not as big because, so what this one did is it essentially canceled out the T2 prime decay due to the inhomogeneous magnetic fields, different magnetic fields in different places. So that guy is called, so that's spin echo, SE1, 2. So that's our standard spin echo. And now, if we didn't do anything else, if we didn't do any additional pulses, nothing would happen. It would just be silent. But let's do another pulse. And so if we do another pulse, say here, it's not the same time spacing as between the first two pulses. So here's a third pulse. So this time here. So what is this time here? So this time here was exactly the same, precisely the same as tau 1, when that echo, the peak of that echo occurred. But let's just put all those times down here too. So here's tau 1. And exactly that amount of time later, the echo comes out. But the time between the second and the third pulse is tau 2. We could have made it the same as tau 1, and we'll see that at the end of the lecture we'll see that that's commonly done, and so that you end up with sort of echoes piled on top of each other. But in this case we didn't, so we made a spacing that was different than tau 1. So sometimes we could call, in my previous notes, sometimes I called this guy tau 3, but you can see that that's equal to tau 2 minus tau 1. Let me put it below space. So this guy is tau 3 equals tau 2 minus tau 1. So when we do that third pulse, we get yet another FID. So there's another FID comes out of that. So that swept all the spins together and made a nice signal. But almost immediately after that, we get another small echo. And so this is the first additional echo that we're getting. So now if you just did 2 pulses, you get 1 echo. If we do 3 pulses, we get an additional echo, and that additional echo comes out this distance away, the tau 3 distance away. So that distance away, like right here, there's another echo that comes out. And it's a kind of a small one. These echoes can sort of pile on top of each other. So if you adjust something, if you adjust some of these timings, what happens? You could cause that echo to appear in the middle of the FID. That's okay. That can occur. So here's this other little echo that appears here. So what causes that one? So that one's called a secondary echo. So why is that a secondary echo? This is a secondary echo. So we'll call it like this, secondary. So what caused that one? So this one, this was FID, free induction decay 1. This was FID 2. And this guy was FID 3. Then we've got that secondary echo. So if you look at this echo here, that echo, the right half of it looks like an RF. It looks like an FID from an RF pulse, because what happened was, all the spins slowly got back into alignment with each other, and then right at the peak of the echo, it's just as if we did another RF pulse. And then after that, we got another actual RF pulse. And so this pseudo RF pulse plus this actual RF pulse makes an echo. And so the time to this is basically just tau 2 minus tau 1. So we get another little echo. And then we get a really big echo. And this one's a little harder. This one's called a stimulated echo. And this only occurs when you need a minimum of 3 pulses to get a stimulated echo. And so what's a stimulated echo? So this one occurs, again, this was just figured out by just changing the timing between the pulses and just seeing what happens, just seeing where the echoes go to. And so this one occurs at a time tau 1 after the third pulse. So here's tau 1, which is we'll use it over here. So it's the spacing between the first 2 pulses. And so that amount of time after the third pulse, so right here. So let me put this down here. So tau 1 amount of time after the third pulse, you get a really big echo. So you get this really large echo. And this one, so what's causing that one? So that's called a stimulated echo, because it only appears if you kind of do a third stimulation. And so how to think about this? So one way of thinking about it is that this guy, if you read an MRI paper, they'll call this one STE for stimulated echo. So stimulated echo 1. There's only one stimulated echo. So this guy is a stimulated echo, and it's quite big. It's bigger than the secondary echo. So what's going on here? So the idea is that when you did tau 1, so let's just say we did a tau 1 that wasn't exactly 90, and so what's going to happen is you're going to get this much transverse magnetization, and then you'll have some, there'll still be some remaining. So this guy is, MT for transverse, XY, and this guy is some remaining longitudinal. So this guy doesn't have to be exactly 90, but it's going to turn some of the longitudinal into transverse. Not all of it. So there'll still be some longitudinal left, but it's going to turn a good amount of it into transverse. So that's okay. So then we do number 2, the alpha pulse 2, and so what does this do? So now we've got some situation where we've got some, longitudinal as well as some transverse, and we're doing another pulse. And you can sort of think of that pulse, that second pulse, as turning some remaining longitudinal into transverse, but then you can also think of it as turning some of the the transverse into longitudinal. So it sort of does both things. And so we'll say leftover invisible transverse magnetization, because we might be in this situation here where this transverse magnetization is there, but you can't see it because it's all sort of dephased. It's all going in different. The local B0 differences caused it to spread out into all different places around the disk, and so it's there, but you can't see it. But some of that leftover invisible transverse magnetization gets flipped into the longitudinal plane. Flipped into longitudinal. So, and when we do that, we could say that it's kind of saved. And why is it saved? Well, if it's longitudinal, then it's not subject to all the jostling. That's the way, we're sort of, it's kind of an abstract way of thinking about what's actually going on, but we take some of that invisible transverse magnetization, turn it into longitudinal, and next advanced lecture we'll go on how to actually diagram this all out, because you can see it's turning into quite a mess, which is the reality of what actually happens whenever you do like a whole series of pulses. But when we save it, it doesn't decay. So saved, and so it doesn't decay. It actually decays it still decays, but it decays much slower. So decays much slower, according to T1. So it's not regrowing. It's actually still decaying, but it's decaying with a T1 time constant instead of a T2 time constant. And the T2 time constant is like 1/10 of a second or 1/20th of a second, so it's it really drops off very quickly, whereas the T1 constant is like 2 seconds. And so it decays much slower, so that's why it's saved. And then, but it's invisible. That part's saved, but invisible, because this guy is longitudinal magnetization, and longitudinal magnetization doesn't make any XY signal that the RF coil can pick up. So it's saved, but if you don't do anything else, so if you didn't do another pulse, so the situation I'm talking about has already happened. It's already happened over here, immediately after the second pulse. Immediately after the second pulse, you save some of the magnetization in the longitudinal axis here. And if you didn't do anything else, you would get the spin echo from rephasing the guys that had gotten out of sync over here. But then that saved magnetization wouldn't be visible. It would just die away. The magnetization would just die away, and you wouldn't see any other signal. But if you do a third pulse, so if you do this third pulse, then what we can do is flip some of that saved longitudinal magnetization back into the transverse plane. And since we're effectively sort of flipping it over, flipping some portion of it over, we'll end up with the situation where the guys who were behind are ahead, and the guys who were originally ahead are now behind, the guys that were originally behind are now ahead, and so then you'll get an echo. So it's kind of like a spin echo. So the amount of time, so what is it, how did they figure this out? Well, they just did if you just do like a pulse here, and a pulse here, and then a third pulse, what happens is, that amount of time after the third pulse, you get the echo. So here's where the echo occurs. And you can, if you just put these pulses closer together, then the third pulse, this guy will, the echo will occur exactly where you'd expect it to. The same amount of time between the first and the second pulse after the third pulse. So if I moved this pulse closer this way, it would move this echo closer this way. So it looks like a spin echo. It's kind of like a weird spin echo that has a delay. So you save the magnetization, and so it no longer was dephasing. That's the saved part. But it was invisible because it was longitudinal. And then the third pulse flipped it back into the transverse plane, where then it could start canceling delays, and it makes this big echo. And so the fact that the echo is very big is kind of a positive thing, because it's very big after a long period of time. It can be just as big or even bigger than this spin echo. Okay, so this is, flip, some, doesn't have, depends on what the flip angle is, some saved ML back into transverse, and then, rephasing occurs. And you get an echo. But that's not the last of the echoes. There's still more echoes. So the next echo is, we did 2 pulses here. So you can see like the first and the second FID. And so that time is, I already have it written up there, but I'll write it down again. So that time is tau 2. That's the time between the second and the third. So if we go that amount of time later, then we're going to end up with another spin echo here. So because that's the same situation as 1 and 2. So tau 2 time after the third pulse, and we get another echo. It's a smaller one, so it'll be another smaller one. And so this guy is spin echo 2, 3. So this is stimulated echo 1, 2, 3, because you need all the pulses for that one. And then, last but not least, we did pulse 1 and pulse 3, and so pulse 1 and pulse 3 will make a we'll make yet another spin echo. And so that one, so here's pulse 1 and pulse 3. So that time is t1 plus t2. Tau 1 plus tau 2. And so that amount of time afterwards, there's going to be yet another spin echo out here. So, and then finally it's quiet. So that's the last one. This one's pretty small. So this is a little spin echo. And so this is spin echo 1 and 3. And so that comes in exactly at time tau 1 plus tau 2. So 3 pulses will give you 4 echoes after the pulses end, and then another echo in between before you did the third pulse. So there's an equation for how many echoes you get, and so the equation is the number of echoes is equal to 3 to the n minus 1 minus 1 over 2. So this is this guy here is the number of RF pulses. Number of RF pulses. And so what does that equal? Well, 3 RFs, that's what we did. 3 RFs gives 4 echoes after the third pulse. 6 RFs, we might do 1,000, but 6 RFs gives 121 echoes. So you can clearly see this is one of the reasons why pulse sequences are often kind of very regular. They're very regular because what you're trying to do is sort of get the echoes all sort of like sitting on top of each other, so that we don't have sort of random echoes appearing in random places and messing up the data. So it turns out the problem isn't, it's actually extremely easy to make echoes. The problem isn't making echoes, the problem is sort of managing all these echoes when you're doing thousands of pulses. And you might be doing, just to get some idea of how many pulses you're doing, you commonly in say a gradient echo sequence, like a high resolution anatomical scan, you might easily be doing 100 pulses a second. So if you plug 100 into here, you'll get millions of echoes that are happening. And so this is something that has to be managed. Now, there are special uses for stimulated echoes, because an example might be if you make some kind of measurement, maybe like a diffusion measurement. You want to sort of measure what direction atoms are diffusing in. One of the problems with that kind of a measurement is you've got to wait a while for the diffusion to occur. And so if you wait a while, well, if I wait long enough, my spin echo is going to get pretty small. But since the stimulated echo doesn't decay as nearly as quickly because it's temporarily saved, you can use that to actually make a measurement where you need to make a measurement that allows some other process to happen, like diffusion. And so a stimulated echo could be useful for that, where you'll essentially get a bigger signal at a later point in time. Because the problem is always about the signal to noise, because if I do a spin echo like this, then I can get some signal. But if I move the 180 out, the spin echo is going to decay down according to e to the minus t over t2. And so if I go out, if I go out a long distance so that the echo occurs after diffusion has had a chance to diffuse, well, maybe there's no signal to record. And so that's some of the considerations that you would keep in mind. And when we talk later about practical sequences that people use, there's one practical sequence that has like tons of stimulated echoes in it, and that allows us to do these very high resolution scans with very small voxels because the signal is so much bigger. And I'll talk about that later, but let's just stop here for a second. And so any questions? This is the classic sort of three RF pulse diagram of so one FID, another FID, spin echo occurs, third FID, secondary echo, which is the spin echo acting as if it was an RF pulse, and then the stimulated echo, which is this weird saving business that requires 3 pulses, and then another spin echo from 2 and 3, and then a final spin echo from 1 and 3. Question?
Yes, where are the echoes coming from?
Where are they coming from? Yes, okay, so that's the main lecture, but where they're coming from, what you can think of, the simplest way of thinking of it is, you do an RF pulse here, and then the T2 prime decay, that's the one that's caused by the spread in frequencies, which is caused by this slight spread in the local B0 field. So all different parts of the sample. It could be a small part, like just like a millimeter or something like that, and that one has a slightly different magnetic field from the neighboring one, different B0 field, and that's going to cause the precession to occur at slightly different frequency. And so what will happen is all these slightly different B0 field strengths will cause the local magnetization vectors to get out of sync with each other. And so they'll all slowly get out of sync with each other until they're, initially they'll just get a little bit, but over time, like over here, they've gotten quite out of sync with each other, and so they cancel each other out, even though there's still magnetization left. And then the fundamental idea of an echo, you just take this guy, and you just, like that, you just take this guy and you just flip it over 180 degrees. And so if you flip all the spins over, what will happen is whoever got the furthest behind is now the furthest ahead. And so then what will happen is, over exactly that amount of time, all the guys that had now gotten behind will slowly start getting ahead, and they'll exactly all come together at an echo time, which is exactly the amount of time between the 2 pulses. So what it is this is the recoverable T2 prime magnetization. So remember it was 1 over T2 star, which was everything glommed together, equaled 1 over T2 prime. That was the static, this dephasing caused by the static B0 differences added on to the dephasing that we can't fix, which was caused by just the jostling business. And so this guy is the recoverable one. So recoverable with an echo, meaning like recoverable with another pulse that will sort of flip the whole thing over and cause the people who were the most behind to now be the most ahead. So so I mean what it means is even though there's no signal, right, at this point there's a bunch of magnetization still there. And if we didn't do anything else, it would just disappear, you would never see it. Because it would just continually get even more out of phase, and it would all add up to 0. It's when you think about these things, it's a little strange, but it's like I said before, it's almost easier than a macroscopic object because the spins are all exactly the same. the weight of the protons are all exactly the same. And so when you have situations like that, you have these like really sort of almost easy to understand things like the echo. There's no friction messing things up. It just, you just move this pulse out and this guy just marches out exactly. Because there's no variation in the spins or the strength of the magnetic moments. Everything is just all fixed. And so it's actually sort of easier. Quantum mechanics is kind of weirdly easier than sort of macroscopic mechanics because of the quantum nature of spin and the fact that protons all weigh exactly the same thing and electrons all weigh exactly the same thing.
Just to follow up, so you send a transmit RF
Yeah.
to the body coil, and then you have your receive coil over the head, and the body itself, the proton, will send the signal back up to that receive coil. The actual echoing is occurring within the body, within the...
Yes, yeah. The actual echo is coming out of the sample. So, I mean, in the old days, you can record with this transmit coil. That's the way they used to do it. They would just transmit with the transmit coil, like transmit a little pulse and then quickly flick it over to, like you can flick it over in like a millisecond or so, standard one, or 2 milliseconds. You can suddenly flick it over and then start recording immediately. And then, so these things are, the FIDs are coming out of the head that have to be sort of received from an RF coil. So this is, so we should label this. This is, our RF stim, and this guy is our radio frequency record. Could be the same coil, just alternating back and forth. But yes, so all of these things that I drew here in green are just coming out of the sample, also known as the head, yes, usually. Yeah, and then these things are just those little, very brief, these could only be like, it might be like one, less than a millisecond, could be like, 100 microseconds. So just a tiny little burst to stimulate. Any other questions? All good on the echoes? Okay.
So in pairs of 3, you get a
Stimulated echo, yeah.
Can you get, if we set another stimulated RF pulse, say we'll call it alpha 4,
Yeah.
would you get a stimulated echo from 2, 3, 4?
Oh, absolutely, yes. All the possible combinations. There'd be multiple stimulated echoes because, if you did a 4th pulse, now you're going to have, a stimulated echo from pulse, 1, 2, and 4, and 1, 3, and 4. So you're going to get, you'll get a series of stimulated echoes. And like I said, if you do 6 RF pulses, you get 121 echoes. So, lots of echoes. So what's an actual sort of practical pulse sequence that's heavily used? And like I said before, one of the ideas is why don't we just do something a very regular sequence, because we've got these echoes and the echoes come out on a kind of a regular basis. And so one of the first things they did, this was long before MRI, this was just, they were doing this for just doing NMR of chemical samples, is just do a sequence of RF pulses that are evenly spaced with one variation. So this one's called, what? CPMG. There's like 4 guys: Carr, Purcell, Mayboom, and G. I don't know who G is. He was the last name. So this is an echo train. So this is a spin echo train. And so what we do here is do a series of RF pulses, and in this case we're going to do 180s, special case 180s. And so the first, so this is, RF stim. So the first pulse is a 90-degree pulse. And so, and then we have, how much time do we need? About 6 of those, so okay, that'll be good. So at this point, do a 180. And so if we look at the signal coming out of that, there'll be a big signal here out of the 90. So just 190. So let's make it a little bigger so that we can decay it reasonably. Okay, so there's a big signal coming out of the 90. And if everything went right with our 180, 180s are often slightly imperfect, and so there might be a little signal coming out. But if everything went perfectly right, there should be no signal coming out of the 180 because there's no transverse magnetization. So we waited a long time. So this guy is, RF. So RF stim. This is RF record. And before here, wait. So we wait a long time so that everything got fully magnetized again, so there was no non-equilibrium situation. So you wait a long time, do 190, just 190, and then there'll be a spin echo that will occur. So here's the tau 1, and so we wait for tau 1 distance away, and then at that point there'll be a strong spin echo like that. But now we'll take advantage of the fact that that guy sort of acts like an RF pulse. You can sort of think of this one as acting like an RF pulse. And so let's just do another 180, so that's spaced another tau 1. So these two are closer together. These are twice as far apart. And so if we do another 180 here, so if we didn't do anything else, the signal would just disappear. There'd be no signal after that. And so if we do another 180, if it's a good 180, nothing should happen. And then because this thing sort of looks like an RF pulse, everybody's lined up again, and we just did another flip, another RF stimulation after that, then that amount of time later, you should get another echo. And this echo won't be as big because it will have had more T2 decay. So this is a smaller, but it's still better than nothing, because otherwise there would have been no signal there at all. And you can keep going on. So if we wait another 2 times tau 1, and then do yet another 180. These guys are all 180s. Then you get another echo. And you could keep doing this. I spaced it out so we could sort of see it clearly. But so again, another 180, nothing happens. But if you wait, tau 1 after that, then you get another echo. And so if you actually sort of plot this curve, what you're seeing is the peak, the very peak of the echo. So that that curve is e to the minus t over t2, because that's the unrecoverable loss of transverse magnetization. Whereas this curve here, this is the e to the minus t over t2 star curve. And this one will be, this curve would be e to the, minus t plus this distance, this distance subtracted off of t, right? So it would be, e to the minus t minus 2 times tau 1. And so that there'll be a different equation, but it will still fall off as a function of this t2 star time constant. So you can do, and what are you actually, so this isn't, you don't record the whole mess. So this is signal. What are we actually recording? Usually what we do is we just turn on the recorder just for the echo parts. So typically, this is RF record. This is what you actually save. So you just throw away the FID, don't record anything from the FID, and then when this echo is occurring, make a whole bunch of recording data points like that, and then turn off the recorder, and then another echo is occurring. And so, you record a little burst of data and another little burst of data like that. So that's what you would actually, that's where all your data points, so you might, record, et cetera, to, for example, 16 echoes. So you might record like 256 data points times 16. So you could, remember, we've got to get up to millions. So you could easily do 16 echo trains. If you squished everything together, you could sort of collect them a little faster. So, and why do we want to sort of extend it out? Just to, reemphasize again, we're looking for contrast. And so if we have, one tissue type that's falling off like that, if we make the echoes really early, there's not going to be any difference between two tissues that have two different T2 values. So what will happen? So they'll both start at the same value, and then they'll both end at 0. But if you record very early on, you get a big signal, but there's no difference between. So this is like T2A, and this is T2B, two different tissue types. It's sort of like, so let's say this is gray and white matter aren't very different, but we'll just call them A and B. And so what you want is like somewhere in here. So the thing is, you need to wait a reasonable amount of time, and this is using something like this is another way to sort of wait a reasonable amount of time, but still get a decent signal. So it's commonly used when you want to get one of these later, smaller signals to be very strongly weighted by the tissue contrast between two different T2 tissues. Because if you squished everything in right at the very beginning, no contrast. You might want that, like if you're trying to record proton density. Well, we'll talk about all the different ways of messing with the contrast, but this is a commonly used one. Okay, Stan, I'll stop the recording there so I don't accidentally start the next lecture recording. Okay, so any questions? I can take questions after the recordings if there's any questions about the spin echo train.